Capacitors are one of the most fundamental electronic components we use. You would have to look very hard to find a circuit which didn't have a capacitor in it. But do you really know about capacitors? Stay tuned till the end, as this video covers all the fundamental aspects of capacitors. The capacitor symbol has two lines, either flat or curved, representing how the capacitor is made. A curved line indicates it's polarized, likely an electrolytic capacitor. If the symbol lacks polarity indication, it's likely a non-polar capacitor. Let's explore the internal components of a capacitor. By delicately removing the outer plastic label and metal cover, we can reveal multiple layers of rolled paper inside. These layers can be carefully unrolled and separated. This rolled paper comprises two or more parallel conductive metal plates, each of which is connected to a terminal wire. These wires serve as the connection points to the rest of the circuit. Importantly, these parallel metal plates do not physically touch each other. Instead, they are electrically isolated by high-quality insulating material layers commonly referred to as the dielectric. The symbol representing a capacitor precisely illustrates this arrangement. Two parallel lines within the symbol represent the conductive plates, and the space between them signifies that the plates are separated by a dielectric layer. Using the water analogy, we can understand the behavior of capacitors more easily. Imagine two pistons, each containing water, connected by a pipe. When we apply a constant force to piston A, water starts flowing to piston B due to increased water pressure. This phenomenon is akin to the flow of electric current in a circuit. When a battery is connected to a circuit, electrons move from the negative terminal to the positive terminal. However, in the context of electricity, we consider current to move from the positive terminal, high potential, to the negative terminal, low potential. Now picture this. We've got a flexible, elastic chamber sitting in the middle of a water pipe, kind of like a water balloon trapped between two pistons. On one side, we have regular water. On the other side, green-dyed water. The two never mix, thanks to a special membrane that acts like a watertight barrier. This membrane doesn't let water through, but it can stretch, just like the dielectric in a capacitor. When you push on piston A, the pressure increases. That pressure stretches the membrane, allowing energy to be stored as it flexes. Eventually, it stops stretching. Why? Because the elastic force pushing back equals the force you're applying. Just like a fully charged capacitor, it reaches a balance and says, "No more, I'm full." Now that we've stored some energy in the membrane, if we disconnect the pistons and connect the two ends of the chamber, the membrane can move the water in the opposite direction and return to its initial state on its own. Initially, we store energy in the device, and then we can use the stored energy to do useful work. We can plot the membrane resistance force over time. Now let's examine the process in slow motion. Initially, the resistance force is 0. When we apply an external force, the resistance force doesn't increase instantly. It begins from 0 and then rises rapidly. However, as the membrane starts to expand, the rate of increase of the elastic force decreases over time until it matches the applied force. Now let's remove the pistons and connect the two ends. The force begins to decrease rapidly. However, as the membrane starts to contract, the rate of decrease of the elastic force slows down over time until it becomes 0. Can you predict what occurs with the water flow during this period? Initially, the membrane is in its resting state, almost as if there is no membrane present at all. Consequently, even a slight force can move a significant amount of water through the pipe. However, as the water begins to move, the membrane expands and starts to exhibit resistance to the water flow, causing it to gradually decelerate. This process continues until the water flow eventually comes to a halt. If we remove the pistons and connect the two ends of the chamber, the membrane can move the water in the opposite direction and return to its initial state. Initially, a significant amount of water flows in the opposite direction. However, as the membrane begins to contract, the force decreases, causing the water flow to gradually decelerate. Let's compare these two situations. Understanding this water analogy will help you better understand how capacitors work. The negative water flow indicates the water is flowing in the opposite direction. When we push water into one side of the chamber, the same amount of water moves out from the other side. It might look like water is flowing straight through the chamber, but it's not. That elastic membrane in the middle, it doesn't let any water pass through. It just stretches and compresses, pushing back with force. So even though the flow continues, nothing actually crosses the barrier. It's all about pressure changes and movement around the membrane, not through it. This is exactly how a capacitor works. It doesn't let current pass through. Instead, it stores and releases energy by reacting to changes in voltage. When we connect a capacitor to a battery, here's what happens. At first, the capacitor voltage is 0. Over time, the voltage gradually increases until it matches the supply voltage. If we disconnect the battery and connect the two ends of the capacitor through a resistor, the capacitor voltage starts to decrease quickly until it becomes 0. Now let's consider the current. In the beginning, the current is high. However, as time progresses, it diminishes and eventually reaches 0. If we disconnect the battery and connect the two ends of the capacitor through a resistor, a significant current starts flowing in the opposite direction. Over time, this current diminishes and becomes 0. Here, voltage behaves similarly to the membrane force, as seen in the earlier example. Similarly, current behaves like the water flow in the analogy. Let's explore this further. Imagine a battery with positive and negative sides. The negative side holds a surplus of electrons, leading to high electron pressure. In contrast, the positive side lacks the same number of electrons, creating a lower electron pressure compared to the negative side. This difference in electron pressure is known as the potential difference, measured in volts. Let's turn our attention to the capacitor. It consists of two metal plates separated by an insulating layer that prevents electron flow. Initially, both plates have an equal number of positive and negative charges, resulting in a neutral state with 0 total charge. Therefore, the electron pressure on the plates can be seen as 0. Let's connect the capacitor to a battery. Focus on the right side of the circuit. Electrons from the negative side see that the capacitor's plate A has less electron pressure compared to the negative side of the battery. Thus, they try to move towards plate A. Similarly, on the left side, electrons in plate B of the capacitor move towards the positive side of the battery, attracted by the lower electron pressure. Remember, the electrons can't cross the insulating layer, so as one plate gains an electron, the other releases one. As plate A gains electrons from the battery's negative terminal, plate B loses electrons to the battery's positive terminal. Electrons flow into one side and out of the other at the same time. This creates the illusion of a continuous current flowing through the whole circuit, even though nothing is actually passing through the capacitor itself. Let's examine the changes in electron pressure. I'll represent the electron pressure of each end using scales. Initially, there's a significant difference in electron pressure between the battery and the connected plates. This prompts electrons to move towards regions with lower pressure. Consequently, the electron pressure increases on one plate and decreases on the other. As the electron pressure difference diminishes, the electron speed slows down, causing a decrease in current. Eventually, when the voltage across the battery and the capacitor becomes equal, the current stops entirely. This clarifies why the voltage difference between the two plates begins at 0 and gradually increases. It also explains why the current decreases over time and eventually reaches 0. It's important to note that as electrons move, the battery's voltage undergoes a slight change, but this alteration is minimal and can be disregarded compared to the capacitor's voltage change. Now let's remove the battery and connect the two ends of the capacitor through a resistor. Initially, there is a significant electron pressure in plate B and a very low electron pressure in plate A. Consequently, electrons rush towards plate A through the resistor, resulting in a high current but in the opposite direction. Over time, the electron pressure difference decreases, causing the electrons to slow down gradually. When the pressure difference reaches zero, the current stops. Now that we have a basic understanding of capacitors, we can explore their behavior further. When we store energy in a capacitor, it is known as capacitor charging. Conversely, when we use the stored energy, it is termed as capacitor discharging. We'll explore the mathematics of capacitor charging and discharging more thoroughly later in this lesson, so for now, just get a general sense of how it works. With that basic understanding in place, let's move on. We've modified our circuit to observe capacitor charging and discharging. Initially, both plates are charge neutral, resulting in zero capacitor voltage. If we turn on switch S1, current will flow, and the capacitor will start to charge. Let's consider what happens in detail. When one electron moves to plate A, its charge becomes -1. And another electron leaving plate B brings its total charge to +1. This slight difference in charge causes an increase in the capacitor's voltage. Continuing this process alters the total charge on both plates, consequently increasing the capacitor's voltage. The coulomb is the unit of electric charge in the International System of Units. 1 coulomb is equal to approximately 6 quintillion positive or negative charges. The capacitance of a capacitor is the amount of charge, measured in coulombs, needed to change the voltage across the capacitor by 1 volt. Capacitance is measured in units called Farads. Let's assume this capacitor needs Q coulombs of charge for each plate to change its voltage by V volts. We can find the capacitance of this capacitor by dividing Q by V. The capacitance of a capacitor is typically labeled on the component, along with the voltage rating and other details. For instance, a capacitor might be marked as 100 volts and 470 microfarads. This means the capacitor has a capacitance of 470 microfarads. In simple terms, it requires 470 microcoulombs of charge to change its voltage by 1 volt. The voltage rating indicates the maximum voltage the capacitor can handle without getting damaged. In this case, the capacitor can withstand up to 100 volts. Some tiny ceramic capacitors have 2 to 3 digits code printed on them. The first 2 numbers describe the value of the capacitor, and the third number is the number of zeros in the multiplier. When the first 2 numbers are multiplied with the multiplier, the resulting value is the value of the capacitor in picofarads. If there are only 2 numbers, it means there is no multiplier. You can read the value of the first 2 numbers in picofarads. Let's revisit the construction of the capacitor. It consists of 2 metal plates separated by an insulating material layer. The capacitance, or how much charge the capacitor can store per volt, depends on 3 key things. First, the surface area of the plates. Bigger plates can hold more charge. Simple. Then the distance between the plates. The closer they are, the stronger the electric field, so more charge can be stored. The permittivity of the dielectric. This is basically how well the insulating material can support an electric field. Different materials have different capacities. We can calculate a capacitor's capacitance using this formula. Capacitance is equal to the permittivity times surface area divided by the distance. Now, here's the important part. Units matter. Permittivity should be in farads per meter. Area should be in square meters, and the distance should be in meters. Use the right units, and your answer will come out in farads, the standard unit of capacitance. So yes, double-check those units. Now let's break it down. If you increase the plate area, capacitance goes up. If you increase the permittivity of the insulating material, capacitance also goes up. But if you increase the distance between the plates, capacitance goes down. So what kind of permittivity are we using here? In this equation, we're using absolute permittivity, which measures how well a material can allow electric fields to pass through it. But most textbooks don't give you that directly. Instead, they give you relative permittivity, also called the dielectric constant. It's just a ratio comparing your material's permittivity to that of empty space. A vacuum. And the permittivity of free space is always 8.854 times 10 to the power of negative 12 Farads per meter. So if you're given the relative permittivity, just multiply it by 8.854 times 10 to the negative 12 to get the absolute value you need for the formula. Capacitor math isn't too scary, as long as you don't let the units sneak up on you. All right, let's talk about series and parallel capacitors, because how you connect them totally changes how they behave. Let's start simple. Imagine a single capacitor connected to a battery. Let's say it needs Q1 amount of charge to reach the battery's voltage, Vs. As we've learned, capacitance is the ratio of charge to voltage. Now, what if we want to add another capacitor to this circuit? Well, we've got two ways to do it: series connection or parallel connection. And here's the cool part. The total capacitance changes depending on how you connect them. So let's break down what happens in each case. Let's consider the parallel arrangement. Imagine both capacitors are connected to separate batteries like this. Suppose to increase the voltage up to the battery voltage, C1 needs Q1 amount of charge, and C2 needs Q2 amount of charge. We can express the capacitance of each capacitor using their charge and voltage. Let's rearrange these equations to make Q the subject. Now, instead of two batteries, if we connect both capacitors to one battery like this, C1 still needs Q1 and C2 needs Q2 to reach the supply voltage level. So, what's the total capacitance of this circuit? To figure that out, imagine replacing both C1 and C2 with a single magical capacitor, let's call it C3, that does the exact same job. This means C3 must store the same total charge. That's Q1 plus Q2, and reach the same supply voltage. Now here comes the key part. Capacitance is charge divided by voltage, so for C3 we can write Q1 plus Q2 divided by Vs. But wait, we can express Q1 and Q2 using the original capacitors. Now cancel out V's, and boom, C3 equals C1 plus C2. So the big idea here? When capacitors are in parallel, their total capacitance is just the sum of the individual ones. In a series capacitive circuit, the same displacement current flows through each part of the circuit. Let's examine this more closely. For clarity, let's name the plates as P, Q, R, and S. If one electron moves from the negative side to plate P of C2, one electron has to leave plate Q to plate R of C1. This process continues, where to accumulate one electron on plate R, plate S has to release one of its electrons. These electron movements occur simultaneously. Hence, each plate always holds the same amount of charge. Now here's the next big thing. In a series capacitor circuit, the applied voltage doesn't just hit one capacitor, it gets divided across all of them. So if the total voltage from the source is Vs and it's applied across two capacitors, then Vs is equal to V1 plus V2. Now let's dive into calculating the capacitance of each capacitor, starting with the fundamental relationship. For capacitor C1, this gives us C1 is Q divided by V1, and for C2, it's C2 equal to Q divided by V2. But to understand how the total voltage divides across the circuit, we want to isolate the voltage in each case. So now we have two neat expressions for the voltage drops across the individual capacitors. both in terms of the same charge and their respective capacitances. As we mentioned earlier, Kirchhoff's voltage law tells us that the total voltage rise around a closed loop must equal the total voltage drop. That means the voltage supplied by the source, Vs, is equal to the sum of the voltage drops across each capacitor. Now that we've expressed those drops, we can substitute them directly into the equation. This gives us V's equal to Q divided by C1 plus Q divided by C2, which expresses the supply voltage entirely in terms of the charge Q and the individual capacitances C1 and C2. Now, how to calculate the total capacitance of this circuit? To determine the total capacitance of this circuit, let's consider a single equivalent capacitor that replicates the combined effect of C1 and C2. This equivalent capacitor will have a capacitance value that represents the total capacitance of the circuit. This C3 capacitor has to reach the supply voltage by storing Q amount of charge. Hence, we can represent the capacitance of C3 as Q divided by Vs. We can replace Vs with the charge amount and the capacitance of each capacitor. Simplifying this expression by canceling common factors results in a relationship like this. In conclusion, the reciprocal of the total capacitance of capacitors connected in series is the sum of the reciprocals of each individual capacitance. All right, now that we've got a solid understanding of how capacitors work, what they are, how they charge and discharge, and how they behave in circuits, it's time to level up. Let's dive into the math behind capacitors. In this section, I'm going to walk you through how current and voltage are related during charging and discharging, what the time constant is and why it's so important, and how we can actually use a capacitor's discharging time in real-world circuits. Don't worry, I promise it's not as scary as it sounds. In fact, once you connect the math to the physical behavior we just explored, the equations start to feel surprisingly logical. Let's start by seeing what really happens during capacitor charging and discharging. Here's the setup. We have a simple circuit with a capacitor, a resistor, a switch, and a battery. When we flip the switch to position S1, the capacitor will charge. When we flip it to S2, the capacitor will discharge. To see exactly what's going on, I'll connect a voltmeter across the capacitor to measure the voltage, and an ammeter in series to measure the current. All right, first up, let's flip to S1 and watch what happens as the capacitor charges. Pay close attention to how both the voltage and current behave over time. As we talked about earlier, when a capacitor begins to charge, the voltage across its plates starts rising quickly. But here's the thing, it doesn't keep climbing at the same speed. Over time, the rise slows down, little by little, until eventually, the capacitor's voltage matches the battery's voltage. At that point, charging stops completely. Now let's talk about the current. At the very beginning, the current is at its maximum. In fact, it's almost like the capacitor isn't even there. It acts like a short circuit, letting electrons flow freely. But as the capacitor charges up, it resists more and more. The current starts to drop, gradually getting slower and slower. And when the capacitor is fully charged, the current falls all the way to zero. At that point, the capacitor behaves like an open circuit. No more current can flow. Now let's flip the switch to discharge the capacitor. And this time, the story runs in reverse. At the start, the voltage is high. It's sitting at the full supply voltage. But as the capacitor discharges, the voltage drops rapidly. Over time, the drop slows down until the voltage finally falls all the way to zero. And what about the current? Well, now it flows in the opposite direction. It starts off large and negative, almost like the capacitor has turned into a short circuit again. But just like during charging, the current gradually shrinks in magnitude, slowing down bit by bit until it eventually reaches zero. At that point, once again, the circuit behaves like it's open. No current, no voltage. If you look at the voltage and current plots for charging and discharging, you'll notice something cool. The curves are almost mirror images, and they take the same amount of time. Whether the capacitor is charging up or letting go of its energy, the timing stays nearly identical. Now let's get into some math. Earlier, we defined capacitance as the amount of charge needed to change a capacitor's voltage by 1 volt. And remember, charge is measured in coulombs. The basic relationship is C is equal to Q divided by V. Let's build on that. If we rearrange the equation to make charge the subject, we get Q is C times V. Now here's the important part. During charging and discharging, both charge and voltage are changing over time. So to capture that dynamic behavior, let's take the derivative with respect to time. Since capacitance, C, stays constant, we apply the product rule and get dQ by dt is C times dV by dt. But wait, dQ by dt is just another way of saying current. It's the rate at which charge flows through the circuit. So now we have a super handy equation connecting current and voltage in a capacitor. I is equal to C times dV by dt. This equation shows that current in a capacitor depends on how quickly the voltage changes, not just the voltage itself. Unlike a resistor, where current is directly proportional to voltage, a capacitor responds to the change in voltage. You can clearly see this behavior in the charging and discharging graphs. During charging, the voltage rises quickly at first, so the current is high. As the voltage rise slows down, the current also drops, and once the voltage levels off, the current falls to 0. During discharging, the voltage drops rapidly at first, making the current a large negative value. As the voltage continues to fall more slowly, the current also decreases, and when the voltage reaches 0, the current becomes 0 too. In both charging and discharging, the capacitor's current is really all about how fast the voltage is changing. Now that we understand that, we're ready to dive into our next big topic, the time constant in a capacitor circuit. Once again, think back to the charging and discharging process. When a capacitor charges, its voltage climbs from 0 volts up to the supply voltage. When it discharges, it starts at the supply voltage and gradually falls back down to 0. Now, here's where things get really interesting. The time constant, represented by the Greek letter tau, tells us how fast this change happens. And it's super simple to calculate. Tau is equal to R times C. Just multiply the resistance by the capacitance, and boom, you've got your time constant. But why is this so important? Because when a capacitor charges or discharges through a resistor, something fascinating happens during one time constant. The voltage changes by about 63.2% of the difference between where it started and where it's heading. Let me put it this way. During charging, after one time constant, the capacitor gains about 63.2% of the voltage it still needs to reach the supply voltage. And during discharging, after one time constant, it loses about 63.2% of whatever voltage it started with. It's like the capacitor is racing toward the finish line, fast at first, but slowing down as it gets closer. Let's walk through a simple example to really nail down how the time constant works in an RC circuit. Imagine this setup. We have a resistor with a value of 1 kilo ohm, that's 1,000 ohms, and a capacitor with a value of 1,000 microfarads, which is 0.001 farads. At the beginning, the capacitor's voltage is 0. By the end, it's going to charge up to the source voltage, which is 10 volts. Now, to find the time constant, all we have to do is multiply the resistance by the capacitance. That gives us a time constant of 1 second. In other words, in just 1 second, the capacitor will be about 63.2% of the way to full charge. All right, let's work through the calculations step by step. Our starting voltage is 0 volts, and the source voltage is 10 volts. During the first time constant, that's 1 second, the capacitor will charge up by about 63.2% of the way from where it started toward the final voltage. Since we're starting from 0 volts, 63.2% of 10 volts is 6.32 volts. So, at the end of the first second, the capacitor's voltage will be around 6.32 volts. Already more than halfway there, but still some distance left to go. Let's mark this point on a voltage versus time graph so we can see it more clearly. At 1 second, the voltage reaches 6.32 volts. Plotting it out helps us actually see how the capacitor is racing toward the supply voltage, but still has a little way to go. We can calculate the voltage change during the second time constant in exactly the same way as before, but this time, keep in mind, the starting voltage is now 6.32 volts, because that's where the capacitor charged up to after the first time constant. From there, the voltage rise during the second time constant is about 2.32 volts. Let's mark this on the graph. Starting from the end of the first time constant at 6.32 volts, we now add the 2.32 volt rise. So, 6.32 plus 2.32 gives us about 8.65 volts at the end of the second time constant. Let's plot that point on the graph too. You'll notice how the voltage keeps getting closer to 10 volts, but each step gets smaller and smaller. Now let's do the same thing for the third time constant. This time we're starting from 8.65 volts, the voltage we reached after the second time constant. During the third time constant, the capacitor will gain about 63.2% of that remaining difference, which is 0.85 volts. So during the third time constant, the voltage rise is just 0.85 volts. Let's mark that on the graph too. Starting from 8.65 volts, we add 0.85 volts, which brings us to about 9.5 volts at the end of the third second. You can really see the curve flattening out now. It's getting closer and closer to 10 volts, but never quite touching it. Now, let's do the calculation for the fourth time constant. After the fourth time constant, the voltage will reach about 9.82 volts. If we go one more step, after the fifth time constant, the voltage will be around 9.93 volts. And it keeps going like that. Each time constant gets the capacitor closer and closer to the final 10 volts, but with smaller and smaller voltage changes. By plotting all these points, we can draw a smooth curve that shows how a capacitor charges over time, and that's how we build the classic voltage time graph for a charging capacitor. In our example, we started with 0 volts, but that's not always the case. No matter what the starting voltage is, whether you're charging or discharging, you can still use the same idea. When charging, calculate how much the voltage increases during each time constant and add it to the starting voltage. When discharging, calculate how much the voltage drops and subtract it from the starting voltage. The method stays the same. The only thing that changes is whether you're adding or subtracting. Now let's compare these charging and discharging circuits. In the charging case, the capacitor starts at 0 volts and heads toward 10 volts. After 5 time constants, the voltage reaches about 9.93 volts, close to 10 volts, but not exactly there. Even if we keep calculating for more time, it gets closer and closer, but never fully hits 10 volts. In the discharging case, it's the same story in reverse. If the capacitor starts at 10 volts, after 5 time constants, the voltage drops to about 0.07 volts. Very close to 0, but again, not exactly 0. In theory, a capacitor never fully reaches the supply voltage when charging or 0 volts when discharging. But practically, after 5 time constants, it's more than 99% charged or more than 99% discharged. That's why we can confidently say a capacitor takes about 5 time constants to fully charge or discharge for all practical purposes. Now you should have a solid understanding of the capacitor's time constant. The time constant tells us how fast the voltage across a capacitor rises or falls. And no matter where we start, after 1 time constant, the voltage always changes by about 63.2% of the remaining distance. But where does that magic number 63.2% actually come from? To find out, we'll need to dive into a little calculus. Don't worry, it's easier than you might think. In the last section, we learned how voltage and current are related in a capacitor. Now let's talk about how a capacitor discharges and do the math behind it. We'll start with the basic formula. Q equals C times V. That means charge equals capacitance times voltage. Now, let's take the time derivative of both sides. Since current is the rate of change of charge, we get current equals capacitance times the rate of change of voltage. We've already seen the basic relationship, so let's move on. First, we'll rearrange the equation to make dV by dt the subject, like this. But since we're dealing with discharging, where the voltage is decreasing, we add a minus sign to reflect that. Next, we can replace the current through the resistor using Ohm's law. Current equals voltage divided by resistance. Now let's separate the variables and rearrange the equation. At this point, we have a nice, clean differential equation. To solve it, we integrate both sides, which basically means we're figuring out how the values change over time. After integrating, we get an equation that looks like this. There's a constant, K, in the solution, and we can figure it out using the initial conditions. At time t equals 0, the voltage is V0, so K is equal to the natural logarithm of V0. Now, let's plug that value of K back into the equation and simplify. We can use the logarithm rules here to clean it up even more. Then, by taking the inverse of the natural log, we finally get the complete equation. This is the formula that shows how a capacitor discharges over time. The voltage doesn't drop in a straight line. It falls gradually along a smooth, exponential curve. Now let's do the same thing for a charging capacitor. This time, we don't need to make the current negative, because now the voltage is increasing as the capacitor charges. But there's a small difference we have to be careful about. When we apply Ohm's law, the voltage across the resistor is not just the capacitor's voltage. It's actually the difference between the supply voltage and the capacitor's voltage. In other words, voltage across resistor is Vs minus V. The rest of the steps are very similar to what we did for discharging. This tells us how the capacitor's voltage grows over time, starting from 0 and gradually getting closer and closer to the supply voltage. Now, let's compare the charging and discharging of a capacitor. First, take a look at the charging equation. When a capacitor is charging, the voltage across it follows this formula. Now, what happens after one time constant, when time t equals R times C? At that point, the exponential part of the formula becomes about 0.368. So the equation simplifies to V is V's times 1 minus 0.368, which equals V is V's times 0.632. This means that after one time constant, the capacitor's voltage has reached about 63.2% of the supply voltage. And that's where this magical 63.2% number actually comes from. Now let's think about discharging. When a capacitor is discharging, the voltage follows the given formula. Again, after one time constant, the exponential part becomes 0.368. So now the voltage is V0 times 0.368. That means the capacitor's voltage has dropped down to about 36.8% of its original value, which is a 63.2% decrease. So in both charging and discharging after one time constant, the voltage changes by about 63.2% of the total difference, whether it's going up or going down. I think now everything should be really clear. You know what the time constant is, what it means, and how to calculate it. At first, these ideas might seem a little complicated, but once you start working with them, it becomes much easier. Now, finally, let's look at a real circuit that uses the capacitor time constant in practice. Let's talk about a simple RC timing circuit. In this circuit, there's a push button, and you can connect any load you want, like a light bulb, a fan, or anything else, which is controlled through a relay. Here's how it works. When you press the button, the light bulb turns on immediately. But when you release the button, it doesn't turn off right away. Instead, it stays on for about 1 more minute, and then it turns off automatically. You can even adjust the circuit to keep the load turned on for a longer or shorter time, depending on what you need. So now let's see how this circuit actually works. This is an LM393, a dual comparator IC. Simply put, it compares 2 voltages and decides what to do based on the result. Here's the idea. Let's say the voltage at pin 2 is V2. If the voltage at pin 3, V3, is lower than V2, then the output at pin 1 drops to 0 volts. In that case, the relay isn't energized and the bulb stays off. But if the voltage at pin 3 is higher than at pin 2, then the output at pin 1 jumps up to the supply voltage. In this circuit, that's 5 volts. When that happens, the relay energizes, and the bulb turns on. So our goal is simple. We need to make sure the voltage at pin 3 stays higher than at pin 2 for about 1 minute. First, let's look at the voltage at pin 2. Pin 2 is connected to a voltage divider, so its voltage is fixed at 1.8 volts. That means we need to keep pin 3's voltage above 1.8 volts for 1 minute. How can we do that? Now, pay attention to the capacitor. When we press the push button, the capacitor starts charging through a 1 kilo-ohm resistor. The time constant for charging is RC, which is 1 kilo times 10 microfarads, giving us a time constant of 10 milliseconds. Since a capacitor needs about 5 time constants to fully charge, we only need to hold the push button for about 50 milliseconds. That's a very short time, perfect for a normal push button press. After about 50 milliseconds, the voltage at pin 3 reaches around 5 volts. At that point, the relay is energized and the light turns on. Now, after we release the push button, the capacitor starts to slowly discharge through the 6.2 mega-ohm resistor. As it discharges, the voltage at pin 3 drops down. When the voltage at pin 3 falls below 1.8 volts, the relay de-energizes and the bulb turns off. To find how long it takes a capacitor to discharge from an initial voltage to a specific voltage, I'll use the capacitor discharge equation. Here, Vt is the voltage we want the capacitor to discharge down to. That's 1.8 volts. V0 is the initial voltage, which is 5 volts. The resistance R is 6.2 megohm resistor, and the capacitance C is 10 microfarads. All right, let's do the math. First, substitute all the known values into the capacitor discharge equation. Now, to solve for time t, we rearrange the equation and take the natural logarithm of both sides. After calculating, we find that T over RC is about 1.0217. Multiplying through by RC, we get T is about 62 seconds. So, it will take approximately 62 seconds for the capacitor to discharge from 5 volts down to 1.8 volts through the 6.2 megohm resistor. We can show the voltages V1, V2, and V3 on a graph like this. When the button is pressed, you can see that V3 jumps up to about 5 volts within just 50 milliseconds. If you look closely, you'll notice that V3 actually crosses over V2 almost immediately, even before it fully reaches 5 volts. So the relay turns on as soon as the button is pressed. After we release the button, V3 starts to decrease slowly. And just like we calculated earlier, it will take about 62 seconds for V3 to fall from 5 volts down to around 1.8 volts. At that point, the relay turns off, but even after the relay is off, the capacitor keeps discharging, and V3 continues to fall all the way down to 0 volts. The best part? You can easily adjust the delay time by changing the resistor or capacitor values. Bigger resistance or bigger capacitance means a longer delay. Smaller values give you a faster one. That's all for today. If you think my contents are valuable to the world, you are welcome to join my Patreon community. Like and subscribe to Professor Mad for more interesting videos.